Khadija? Sir, your list.
So welcome everyone to this first live session of the Photonic Integrated Circuits course. Um, so I'll be happy to take any of the questions that you may have. So I already have a few questions here which I'm going to go over, but people who have not submitted the questions earlier, you may do so now. So I'm here to look at those and discuss those questions, right? So you can use the message box here to do that. There are two questions that I have here with me. I'm able to post it. This is from Harsh Saxena. So who's here? Thanks for the question. So I'm glad that you enjoy the assignment questions. So I kept it reasonably simple, right? Not to go too much into the derivation and giving problems to you in finding those. Primarily, they are conceptual. This is intentional. The reason for that is it is important to understand the physics behind the understanding rather than trying to work out based on the formulas that anyway you can do in the present scenario. So once you have a computer and you are connected to the internet, you can always find those. The question here is the technical information that are given online, how reliable are they, right? And how shall we, you know, assert ourselves about the validity of those information? So there are two ways to make sure that your information is legitimate and technically, you know, error free. One is that the source itself. You need to look at the source. So where you are looking this information. So we look at textbooks, for example. Right? So that is another place where you can find this. Instead of going through, paper format, online search and everything is much easier. If it is from a textbook, then probably you will get the right kind of information. You also have a lot of information around when you have people who are writing about this, right? It could be some lectures here, lecture slides, but it could be also from SlideShare. Right? You see a lot of slides floating around, and when you search for it, you will get these slides. But this could be from somebody, like undergrad students who are trying to do some small projects, surveys, and so on. So they would also prepare those slides. So you need to look at what is the source. And if the source is from any lectures given by people who are experts in the field, right, elsewhere, so there could be lectures from some other universities and so on. If you get it there and the source is legitimate, then you are fine. So that is another way of validating, not just blindly, looking at the source like, okay, I have all this information in this particular slide deck, so that means I can, rely on that. It may not be true. Somebody might be doing this as a small project, for example, right? And they perhaps they don't know the technical background there. They are perhaps doing some survey, so you have to be a little careful. So looking at the source is very important. So look at sources that are from lecture series or books or technical reviews. So these are all the places where you will find information more than what you have. So you might have already found that the source is a mix of a lot of things. Right? Sometimes you will find one topic in one single book, like Saleh and Tech is a reasonably basic book. But then we have photonic devices from Liu, which I have mentioned in the references. you can use that. So it's borrowed from all these places. The reason for that is, uh, for example, Liu is built particularly for people who are already comfortable with electromagnetic theory, right? And very deep into the subject, right? For people who are doing photonic IC research, so that becomes very good. But when you are doing course, you just want to make sure that you understand the concepts. That's why I take it and then create the cream, and then that is what we have in this course. So, any books related to guided wave theory, right? Schneider and Lau is one such book, Integrated Optics. It's a very old book, a little difficult to go through because it's old school way of understanding things. But Liu is much more comfortable, and Pollock is also even more comfortable book for you to go through. So these are all the references that you can use, right? But the internet contents are always going to be there. But how reliable are they? It's, as I mentioned, it depends on the source. Okay? The other question here is from uh, Sijus Prasad, who is also here with us today, here in the chat. Um, and I see a lot of people joining in. I would like to welcome you all. Good evening to everyone. So Sijus' question is about the design and simulation of this photonic ICs using computers. Um, So we went through the design phases. There are various designs that we do, right, for these devices. We need to anyway solve the Maxwell equation numerically in order to get this design, right? And once you have this, I mean, how do we design it, first of all? Right? How do we convert this mathematical relation into a solver? In the past, we used to write our own solvers. Right? But these days you get a lot of solvers out there that can do this. We can either do it with finite difference method and finite element method, or finite difference time domain (FDTD). You can do, or finite difference frequency domain. You can also do that. So there are the various techniques that are available to solve these problems, and there are different softwares as well. So it is important to identify a software that you can use, because some of these softwares are also very expensive. So there are free tools also available. There are a couple of free tools, like you have Synopsys. Some Synopsys tools are free. You can have a look at it. And then we have FTTD tools that are available free. And there is one tool called Camphor, which is FTFD tool. This is frequency domain method. So there are tools that you can use in order to do that. So those are all the simulation packages that you can use, like ANSYS. Um, then you have Photon Design. Then you have Mentor. So all these big EDA tool manufacturers are also now bringing photonics circuit simulation and also device simulation packages. So one of these packages should be able to help you in designing the device and so on. So another way to do it is your own, solvers. It's not very difficult, right? You can simply take your, Maxwell and then the final equation, and then you can write your own MATLAB code or Python code in order to simulate this. It will be a good learner, but then if you go for very complex circuits, then it goes beyond, your interest, right? So you will be writing codes for the solver rather than actually designing the device. If your main idea is to design, then perhaps you could take, your uh, package and then use it for design. Okay. That is my comment on that question, Siju. Thanks for asking that. So we have few questions here. This one, okay. Any textbook for photonic integrated circuits? All right. As I mentioned, there are few, right? Uh, if you want to understand the basics, as I mentioned, that Liu is a good book to start with. So that is Integrated Photonic Circuit Fundamentals. So it's actually the book name is Photonic Devices. So it talks about devices. Circuits is very subjective, right? You can make circuit by putting different components together. So if you understand devices, you can understand circuits, right? So just for circuits alone, we haven't really come to a level where we have a separate book like electronic circuits, right? So electrical circuits. There the things are a little different, right? So here the number of combination, the logical combination that you could have is limited and very application specific. So that's why uh, there will be a lot of books on the devices rather than just on the circuit. The book might say photonic integrated circuits, right? But then 90 percentage of the book will be on devices. So you take any photonic devices book, it will also cover uh, circuits part. Okay. So whatever references we have listed in the course, so those are all the things that you can use. Beyond that, you have references, from different folks. Like Professor Lucas got his own book, and Professor Pavisi, Lorenzo Pavisi's book on silicon photonics, for example, right? So there are these popular books, right? But then at the end of the day, whether you want to have breadth or whether you want to have depth, right? So in this course, we try to understand each and every component. So later on, whichever book you pick up, you should be able to appreciate, whatever circuit they are putting out there, and easily understand even the research papers. What are all the feasible areas of research in photonics? So that's a very broad question. Thanks for the question, Manjit Kumar. Uh, so it's a very broad question, right? So you can do quite a lot of things using photonics, right? So photonics is basically, engineering light. So what can you do with light? It's only your imagination is limiting you from exploiting it. So right now, the area that's really being pushed is looking at photonics for quantum technology applications, right? Because intrinsically, photonics is quantum technology, right? So we talk about modes, which are quantized states, and also we talk about photons, which is again dual property that we see. And you can take a photon and define all the three properties. Like I mentioned, you can talk about phase, you can talk about polarization, you can also talk about energy. So intrinsically, photonics is quantum technology. So using this for doing information processing, computing, sensing, all these things are being heavily looked at. So it's a very rich area, and if you're interested, you can also have a look at that. The other areas are a little more conventional in terms of sensing. How do we use light to sense? This is something we will look at in the later part of our course, where you are going to take the photonic circuits that we studied about, and then see how we can develop sensing devices. So sensing again is pretty broad. For example, can we do Raman spectroscopy on chip? Raman spectroscopy is not very easy because the Raman scattering is very, very weak effect, right? Is it possible to enhance Raman signal using guided wave system or photonic ICs? Can we do atomic absorption spectroscopy, right? Fluorescence. Can we do all this on a chip, right? For doing bio and agri related sensing. So these are all the areas that are very relevant, right? That are useful to the country right now, because there are a lot of pressing problems that we have currently, both in food, agriculture, and health. Right? Is it possible to use light to create solution? For example, this COVID, right? For example, is it possible to use light to detect COVID quickly instead of waiting for 12 hours or 24 hours to get the results? Is it possible to make quick tests using photonics? The answer to that is yes, right? But then how efficiently we can do? So those are all the present day relevant problems that we can address. And the next question is from Sandeep Chatterjee. Thanks for your question. What are all the Indian institutes where they do research on photonics, optical computing? Okay. Um, so optical computing used to be a very, very fancy topic, right? When I was doing optical communication back in the days. Um, Optical computing is very fancy because you think that photons travel speed of light, and if we can do processing in speed of light, then that's the best thing that can happen, right? But optical computing is little different. So optical computing, from the optical side, it's primarily addressing more sort of image correction, aberration correction, digitizing, and so on. But when you talk about doing conventional computing using photons, right? If you are considering that, then this optical computing part um, is something that's a little strange, because um, the density, the computing density um, currently that we have with electronics, we won't be able to achieve that using um, light. Using photonics, it's very hard to achieve that kind of integration and processing density. So we won't be able to replace the current day electronics with purely optical processing. But what we can do is we can do a hybrid solution where the actual processing happens in the electronic domain with high density, but then the data that is generated, that transport can be taken care by photonics. Because the main bottleneck today in achieving high speed um, computing, right? That is the reason why you want to go to optical computing, right? You want to do things fast. So the bottleneck there is how do we um, transfer data, right, between different processors cores in order to make the processor efficient. So one way to do that is you still do the processing. The arithmetic and logic unit will be still operating in electronic domain, but then the data that it generates can be converted to optical domain, and then you can transport it with speed of light. So then you can easily process this information, right? So optical computing is going to be done that way. As far as I could see this technology evolve. Pure optical computing perhaps can be limited to just one gate. You can I have seen a lot of papers coming out. We have done this gate, that gate using optical and so on, but it will stop there. But we just can't do very complex computing with just a single gate, right? Uh, but if you look at the other side, quantum computing, that is that is something that we can really bet on. Instead of conventional computing, things that can be done with quantum computers can be efficiently done by using photonics compared to other competing technologies that we have. Also on Sandeep's question on what are all the institutes. So there are multiple institutes. So we have IISc to start with. So that's where I'm sitting right now. Even at IISc, we have different departments looking at different problems using light. Uh, And then we have IIT Delhi, Professor Amol Chowdhury there looks at on-chip, non-linear RSEs and so on. IIT Kharagpur, Professor Shailendra is there, and IIT Indore, where Professor Sumanta Gupta, he does a lot of interesting work on modulators and a lot of interesting devices. And Professor Rajesh Kumar, IIT Roorkee, is also an interesting chap that taking care of it. We used to be lab mates long time ago. And we also have IIT Madras, where they are doing a lot of silicon photonics based work. So these are all the places where a lot of interesting things happen in the country. So the next question is it possible for us to model the wave equation in waveguides in a simulation software? Would you recommend one to start? Yeah, so this is something that Siju Prasad also asked. Is there any softwares that are available? There are many softwares available. I mentioned few of those. Um, you can do that, or you can just use MATLAB. Right? So MATLAB also offers all these solvers. You can easily build one very quickly. You can build one. There are a lot of starting codes already available. The effort is just to search those in the forums. You will get those codes, and you should be able to easily do these simulations. Okay, so my initial thought for this particular NPTEL program was to project, or rather the course was to also have the simulation and so on. But then already you must have seen that the course is really packed, and I don't want the students to be very stressed, that they have to do a lot of assignments with design and so on. But we are thinking of having these design and hands-on courses through some other means, right? So please have a look at our website, Sense, or INUP program that Sense department at IISc runs. So we will be launching that program soon. Actually, the program is launched. We are going to put out the schedule of the program soon. So that program will allow you to do these design experiments and so on. The next question is from Shubhash. Good to see your message here. Thanks for joining, Shubhash. His question is multi-project wafer facility under PIC course, just in line with Professor Luca's course on silicon photonics. Right. So there are, we are, as I mentioned, we are just started this program called PRISM program. This is a photonic IC user program, and the whole idea of this program is to encourage researchers and photonic IC enthusiasts to design devices and engage in this program, and we can fabricate this and give you the chips that you have designed. So that program is already in line. So that's a separate program, as I mentioned, because NPTEL is not the right platform to do that. So we have a separate user program to address this request. Thank you for that question. So another question from Jihan. Uh, So plasmonic structures in this course. So plasmonic structures we don't handle in this course because uh, this course is primarily guided wave optics, not nanophotonics. So plasmonic structures we don't handle in this course. If you want to look at plasmonics, I'm not sure the introduction to photonics course handles this. Um, uh, Perhaps any other nanophotonic course that can handle this plasmonic structures. The reason for this is it is slightly specialized compared to the guided wave system that we handle here. So we are not handling plasmonic structures in this course. Okay. The next question is Bruce. I think beta depends on refractive index. In phase matching condition, beta 1 equals beta 2, how much it's fair? Okay. So that's a very interesting question, technical question. Appreciate Bruce for that, if that is your real name. Um, so beta, let's take beta, right? So what is beta? So beta is a propagation constant. So how do we arrive at beta? So beta takes into account refractive index. So refractive index is a function of wavelength. So already beta captures the refractive index, right, at a particular wavelength. So you also take into account the dispersion, right? So when you talk about beta, you are actually carrying all the information from material to your wavelength to your structure. Everything is, compressed in this beta. So when we say phase matching between beta 1 and beta 2, it is fair because beta 1 and beta 2 collects all this information, optical, structural as well. So it is fair. Another question from Shivash here. May you tell us, sir, what are the thrust areas of photonic integrated circuits in Indian context? What are the potential and immediate limitation to carry forward research work in PIC? So this is something that here Sandeep Chatterjee asked about, right? So that's in line with that question. Um, so probably I covered the areas. Right? We have a lot of pressing needs in the application domain, right? So can we use photonics for food safety? Can we use photonics for agriculture? Can we use photonics for healthcare? These are all the areas where our country needs alternate technology, right? And these are all very advanced technology. So those are all the areas that we have. And the next question is about the limitation, right? So what is the limitation? The limitation is twofold. One is um, you know proper awareness. So we don't have photonic IC courses in the curriculum. It's a very specialized field, but over time this field is going to really become disruptive. So we need to make sure that these courses are reaching our students at early stage, so they are aware of these technologies that are available. So that is one of the key limitations, right? And that's one of the primary reason why we decided to put this 12-week long NPTEL program, right? So that we create awareness, we create interest. So once you create interest, the next thing is you want to do research in this topic. And what are all the possibilities? Of course you can design, because the problems are already there. You can see those problems. I want to solve this, that. You come up with the idea, you come up with a design, but then you have to make it. So how do you make it? And that is where the current day micro and nano fabrication facilities come, because we have micro and nano fabrication facility now spread across the country, including here at IISc. And these facilities are available to anyone in the country. So once you have a good idea, and once you have validated your designs, then you can approach these places that got fabrication facilities, and then get these things fabricated and validated. And once you start validating this, then it becomes a proof of concept, and then you can take it forward for real, field applications and so on. So that's how we close the loop. That is what I see the limitation. But we have to push through, and we have to make ourselves available for all of this, and we are ready to do that. Okay? And the next question is from Manjeet. how we encoded electrical signals are converted into laser sources in transmitter side. Can signals pass wirelessly? Okay, I see there are two questions here. So how do we encode the signal? Um, you will see this, in the active photonics part of the course. Right now we are in week 7, I believe, right? As we move on, we will look at the active devices. So we have passive devices and active devices. In the active devices, you will learn about how to encode electrical signal onto the optical signal, right? And that is by using electro-optic effects, right? So how do we change the propagation of light using electric field, right? So when you change that, then the property of light, like the phase of the light or the intensity of the light, you could change it. And when you change that property of light, you should be able to create this encoding. The other way to do that is direct modulation. That means you change the current that goes into the laser. So when you switch the current, high and low, your output intensity also goes high and low. So that means you have converted the electron flow to photon flow. So that is another way of encoding that you do. Can the signals be passed wirelessly? Of course, yes, because light travels in space. It also travels in vacuum. So there is nothing restricting you to use light for wireless communication. So that is called Wi-Fi, right? Li-Fi, right? Instead of Wi-Fi. So you have light that can be used to transmit like a wireless means, right? So you can use LEDs that can encode the data and transmit the data. So the Li-Fi is very much there, and that is a wireless optical communication. Right? Wired communication is using optical fiber. Wireless communication is Li-Fi, which you can do. Next question is from Siju Prasad. At what point does guided wave optics come into the regime of quantum, and how do we handle it? Interesting question. Uh, Unlike electronics, where you have to reduce the size to uh, to look at the quantum effects in guided wave optics, right? In say in photonic ICs, we are not going to reduce the size of the waveguides. The waveguides are still going to be the same waveguide. But what is different is the wave that is propagating through it. So right now, what we use is a continuous wave. That means a train of photons are passing. It's a continuous wave. It need not be train, right? It will be also bunches, right? So there is huge number of photon flood that goes through the waveguide right now. But in a quantum regime, it will be only one single photon. So only one photon is going to go through this waveguide. So that is what makes things very interesting. Because how this single photon is going to survive all the loss that you have, and also how are we going to use our external forces to change the property or the state of this particular photon in there. So it's all about reducing the photon count, reducing the loss is where your quantum technology when you design photonic ICs for quantum technologies, these things become very important, like single photon emission, single photon detection, reduced loss, whether my polarization of the single photon is kept intact. Is there any change in the polarization, right, when the photon is propagating through it? Whether I can maintain the phase of the photon as it propagates through. So all these questions come in when you use a single photon. Okay, that's in the quantum region. But the waveguide structure and everything remains the same. But when I use it in a continuous wave, that flood of photons, it is all average effect. So I could see some polarization change, but then on an average, my polarization doesn't change. So I won't be able to notice or measure it. But when I take a single photon, any change in this single photon will immediately, be uh, available for measurement. That is a change. Okay, so that is the difference between conventional pick and then quantum pick. Okay, so I probably that answers the question there. All right, so thank you very much, Suhas, for the comments. Appreciate it. Uh, Next question is also from Bruce here. It is better to use animation in this course. It is easy to visualize the subject when animations are included. True, any course for that matter, if we have nice animations, right? Particularly wave propagation, right? It requires a little bit of imagination that you have electrical wave propagating in xz, and then you have yz plane where you have a magnetic field. I completely agree with you. I can't uh, agree more on the need of animation. It's also a matter of how much we could put into it, right? So probably we'll see how much of this we could um, add into the course, and then see in the next uh, evolution. We will try to add some animation for better visualization. Completely agree with you. And it is also interesting that you could write simple Python codes, right, to create this kind of interference and propagation and so on. So that could be very good. Right. Thank you, Harsh, for the comments. We really appreciate you for being here for this discussion. For that matter, everyone who has joined the discussion here, it was very useful, and also I could see, the comments that people are really involved and they would really interested to do something um, with photonic ICs. All right. So, what are the typical skills that an experimental researcher working on photonic ICs or PIC should have? So, let us look at this question in this way. Right? You will only have experimental um, skills if you have done experiments, right? So, if you don't have the right kind of facility in your institute and so on, um, then it is very hard to expect to gain that experimental skill. But what is important is basics. If you want to do thick research, um, then the basic photonics understanding, guided wave understanding, if all those things are right there, then you can approach anyone who's doing experiments, and you should be able to convince them that you have got all the fundamentals that is required, but the only missing piece is experimental skill, because you don't have facility that uh, uh, with which you are able to gain this experimental skill. And if you do get access to this facility, then whatever, right? Like handling optics, right? Handling different optical functional components, putting it together, understanding where the lens should go, where the concave lens should go, where the convex lens should go. How do we understand coupling between lights, and how do we understand fiber? So just those basic skills are good enough. But what is important is, the fundamental idea of the light properties, right? So whether we understand those properties well, and whether we understand the exploitation of those properties well. So that is good enough. Use again define wave vector and wave number to visualize. So wave vector and wave number are, let's say, different things, right? So one is it's a scalar quantity. So it's a number that tells you how strong uh, the uh, the component is, the wave component is, right? But then the wave vector gives you the direction of the propagation itself. Okay, so these two are a little different, right? So one tells you the direction at where it is propagating, right, and its associated components and so on, right? In which direction it is propagating and in which direction the energy is moving. But then the wave number, right, just tells you the strength alone. It doesn't give you information about which direction it is going, right? So these are two different quantities. Uh, so next question is from Zihan. At what point do the waveguide structures we create in fab labs will be affected by scaling? As we are 28 nanometer minimum channel length, how do we effectively couple the light to enter such structures? So it's a fair question, but then as a student of optics, right, you should ask this question. This 28 nanometer is for microelectronics. So this the size of any structure, it should be with reference to the wave function you have, right? So the wavelength of the particle that you are handling. So the electron wavelength is so small, then you can reduce the size of the structures. We can still confine the electron. But then let's look at a photon. When you look at a photon, then the wavelength of the photon, right, is much larger, right? So for example, if you take a visible photon, it will be about 500, 600 nanometer large, right? So you need to accommodate this wavelength. So that means your structure cannot be like uh, very small. So it has to be larger than lambda over 4, um, just to give you an example, right? So less than lambda over 4 is what we call sub-wavelength structures, right? So you need to make sure that this wavelength is is also taken into account. What wavelength am I using? And wavelength of light in the medium, right? It's lambda over n is what we are talking about. If it is 600 nanometers in free space, and if the refractive index is 2, let's say, of the medium that you are using as a waveguide, then 300 nanometer is one wavelength. And when you reduce the wavelength, what happens? You won't be able to confine the light. So this is where when you do a solution to this problem, you will see a very small oscillation inside the structure and very large, you know, decay. So that means the wave is not tightly confined inside. Okay, so we are not going to use this 28 nanometer or 14 nanometer, 7 nanometer structures to guide light. So they are for microelectronics. So our structures are going to be in proportionate to the wavelength that we are going to use. Okay? So that is the difference. So how do we couple the light in and out? That's also in the course. So later on you will see how to do that. Alright. That's a very good question. All right. So are there any more questions? So it's very nice.
Yes, sir, Kim.
All right. right, Jihan has another question. So, like MEMS, there will be a PIC and IC integration. Yes, of course. Um, it's already happening. There are different strategies that people are uh, looking at. How do we integrate photonic ICs with electronic ICs? So I think Jihan, when you say ICs, I presume that it is electronic ICs, right? So we particularly differentiate electronic ICs and photonic ICs, right? So electronic ICs and photonic ICs, we will integrate it wherever it is required, similar to what we do for MEMS. So we have MEMS, and then we need to integrate electronics to do the processing and sensing. So that is indeed true. Another question from Siju here. Can PIC incorporate beyond diffraction limit light transport? Of course, it can. So there are two different ways of confining light. One is in a diffraction limited structure, and then there is beyond diffraction limited structures. So it is possible to confine light, for example, in a plasmonic waveguide. So you could have two metal uh, uh, lines with a very small space that will allow you to confine light within, or two dielectric waveguides and then a space in between that. So this is something that you will see in the sensor section, the application section at the end of the course, where we have actually demonstrated this, where you can confine 1550 nanometer light, right? So 1550 nanometer is the wavelength in 120 nanometer gap, right? So that is, not dielectric guided, that is air guided. Okay, so you can do that. It is possible to do it. There is a boundary condition to match there, right? So once you achieve that boundary condition, you should be able to take the energy and then put it into the this very small space that you generate, which are sub-wavelength. And the other way to do this is you can have sub-wavelength structures. That is called sub-wavelength gratings, right? You have sub-wavelength structures, and they all combine together, right? They act as a compound medium. As a structure, as an isolated structure, they are below diffraction. But then putting them together creates an environment that is in a diffraction range. So you should be able to guide light in such a structure where the discrete structures are below diffraction level, right? But then as a combined medium or combined structure, you should be able to guide light. So there are ways to do that. I presume that answers your question, Siju. The next question is how much important is this? This is from
Shubira.
Shubira. Uh, how much important it is to have computing skills like Python, spins, others. Second, can you kindly share your views on emerging inverse design techniques regarding research and photonics? Very good. Very nice question. So computing skills, it is important, right? Particularly for design, when it comes to design and optimization, one should understand how to do it. But also there is other part of photonics where you are developing technology aspects of it, right? So how do you develop materials, right? Photonic materials. How do you exploit already proven material technology, proven device technology, and create applications out of it, right? So it strongly depends on what your interest is. A basic computing skills is important. So I think that you should try to develop, which is not just for photonics, for any kind of analysis, um, and even for running experiments. You should have some basic computing skills. The second question is about the inverse design. This is a very interesting area that's being coming up, where you you know what you want, but then you do back calculate what the structure should be. So this is primarily driven from this machine learning and AI front, where you give the target and then you work backwards towards the structure that will give you the target. This is very interesting area, very active area of research right now, and with a lot of potential. If you have, in order to do inverse design, you need to have very good computational skills, because inverse design is 90 percentage computation, but 10 percentage is your uh, physics background that will help you to validate whatever you are getting is actually feasible or physically possible, right? So I could have said 100 percentage computational, but at the end of the day you need to have devices that are working, and the device that you could be able to fabricate, right? So that's why I kept that 10 percentage to do the sanity check on this design. What is speed of gamma rays or any rays that is greater than frequency of light? I do not understand the speed of these rays. You can easily calculate from the impedance. The optical photons, we know at what speed they travel, and as you move higher in the frequency range, right? It is going to be the speed of light, right? It's going to be speed of light, but then you create a lot of interesting other phenomena. So there is, I think it's a basic question, but it is speed of light is what they travel. Okay, so frequency as at this point. You elaborate on the positive. This is from Shubhas again. Elaborate on positive and negative slope of group index with respect to increase in operating wavelength in single mode strip waveguide. uh, so this positive and negative slope, you're talking about, the dispersion profile, right? So this dispersion profile is something that you can engineer, in fact. Okay, the positive slope is used in some places and negative slope in some other places. It primarily depends on what you want to do with it. Um, so when you say a single mode strip waveguide, whether it is silicon or nitride, it strongly depends on the cross section. One can actually get a reasonably flat profile, right? Or the positive slope or the negative slope. So all these three regimes are available for you. You can design it accordingly. All right. So it depends on what you want to do with it. For most of the nonlinear things, you need to have two ways. One is you close to anomalous, and you do it, or you want flat dispersion regimes. So where you see interesting things. Even for a lot of mixing, the nonlinear mixing, you try to operate in this zero crossing regimes. Okay. So it is all manageable based on what you want to do actually. All right. Thank you very much for your comments, uh, Siju. We really appreciate it. I hope you guys are having fun attending this course. Um, so there are other courses elsewhere, right? Similar to PIC, which you have to pay quite a lot. We thought, you know, for our folks, we want to offer this course through this NPTEL platform, provide whatever the other courses that are the expensive courses have to offer, right? With all the information and the quality that you guys deserve. All right. So I'm glad that there is a lot of interest, and I want you guys to take it forward and make it more interesting in the country. What are the scopes of nonlinear optics? There is quite a lot of nonlinear optics that you can do. Nonlinear optics. in guided wave system is even more interesting than nonlinear in fibers. The reason for that is this threshold powers are low. You can have reasonably low power non-linearity, provided you have good loss. So when I say good loss, the loss should be reasonably low. When you get low loss waveguides, there are everything that you can do with nonlinear fiber optics. You can do it with photonic ICs. The more interesting thing is you can integrate passive and active devices in those nonlinear platforms. So you can do four-way mixing, you can do spontaneous processes, stimulated processes, right? Amplification process, everything that you can imagine happen in optical fiber can be done in photonic ICs. The other important thing here is you can choose the material. Fiber, there is only silica fiber. There are highly nonlinear fibers which are doped and specialty fibers. But here you can actually take different kind of material systems altogether. You can have silicon, you can have doped oxides, you can use silicon nitride, you can use lithium niobate, you can use barium titanate, you can use titania, you can use alumina, you can use aluminum nitride. There is lot of material system that you can make thin films, make a waveguide, and you have your nonlinear platform. So there is a lot of interesting opportunities in nonlinear. Jihan has a question at the end of the course. What is your expectation from us? Example 21. There are research areas like 2D materials where people research equations. Can we do that for fixed structures? Yes. At the end of the course, what I expect you to learn, right, is to have awareness about this photonic ICs. You should be able to design these simple components, and you should be able to put these components together to build, a circuit for certain application. So that is my expectation because we go through quite in detail about talking about this discrete component. So you should be able to do that. So how long it takes to achieve concurrency of PIC over electronic IC? I quite don't understand uh, the wording here. So if the question is about how long is it going to take to put electronics and uh, uh, photonic ICs together, if that is the question, already attempts have been made and there are demos available where you have an electronic IC and then you have a photonic IC on top, right? Or there is a photonic IC and we have put an electronic IC on top integrated. So this integration, this demo is already there, and there are products that you can buy now, particularly transceiver products, and these products are available right now that has partial integration. Um, it could be on top of each other or they could be side by side. So this sort of 3D integration or 2.5D integration is already out there. When can we expect the start of full-fledged Prism program? So March. So March is the timeline. So end of the March is already so end of March you should be able to see the program for the whole year. So April, right? We are going to have the hands-on and the project call and so on will happen in April. Okay, so that is the timeline that we are looking at. All right, good. I hope you guys had very fruitful session. So if there are no more questions, I think we had a good 1 hour, I believe, session. Very productive. Um, I think this is one of the live sessions in the NPTEL program that we had. Complete 1 hour utilized for discussion. Normally, we don't get that many participants here in the live session. There are a few enthusiasts, but then after 20-30 minutes, it's done. So I'm glad that we had, really lot of interesting participants here, right? Were very committed. I really appreciate your time here and taking this course. I hope to see you. Not hope. I will see you in the next session, which will be communicated. We have 2 more sessions to go. We will see you all soon. So take care of your health, and make sure you follow all the procedures, protocols for your own health and safety, and for others as well. Take care. Um, Good evening. So I was told that you can still ask all the questions that you may have later on in the Google form, right? Or the portal itself, right? I see a very active portal, and I hope the TAs are also responding to that. I see it, every other day to see your queries are answered. Please keep this query coming in so that we have better learning. Okay? Thank you very much.
சொன்ன மாதிரி நீ தான் சார்